Welcome to Two Projects. In this video, we are going to explain the project MCS YOLO, a multi-scale object detection method for autonomous driving road environment recognition. Introduction. So, in the 21st century, the proliferation of vehicles necessitates autonomous driving for safety and streamlined route planning. This technological advancement addresses challenges like accidents and congestion, reshaping the transportation landscape by providing efficient and secure mobility solutions amid the escalating demands of modern urban environments. Early autonomous technologies heavily relied on costly sensor fusion methods. However, the integration of deep learning in computer vision and natural language processing has revolutionized object detection. This transformation ensures an efficient and highly accurate environmental perception system, enabling autonomous vehicles to navigate complex scenarios with precision and reliability. Despite significant algorithmic progress, challenges persist in achieving optimal accuracy and speed in autonomous driving. Acknowledging this, our project introduces a groundbreaking multiscale detection algorithm. This innovative approach aims to strike a balance simultaneously enhancing both the accuracy and speed of object detection in autonomous driving environments. By addressing these challenges, we seek to advance the capabilities of autonomous vehicles for safer and more efficient transportation systems. Object of the project. So, as I mentioned earlier, to enhance the effectiveness of autonomous driving, our aim is to improve the accuracy and speed of object detection within the environmental perception system. This involves tackling existing challenges to elevate the overall capabilities of autonomous vehicles in understanding and responding to their surroundings. And we aim to develop the MCS YOLO algorithm with a coordinate attention module for spatial and cross channel information aggregation, along with a multi scale small object detection structure. We strive for improved sensitivity and precision in detecting 10 small objects, differentiating the MCS YOLO from established algorithms. And the goal is to conduct a comprehensive evaluation comparing the MCS YOLO algorithm against established counterparts such as YOLO V5S, YOLO V4, YOLO V3, YOLO V3 Tiny, YOLO V7, FASTA RCNN, and AD FASTA RCNN. And we want to assess the mean average precision, recall rates, and real time detection speed, aiming for superior results and showcasing the algorithm's effectiveness in automating driving object detection. Requirements needed to execute this project are software requirements. Software needed is Anaconda, primary language used is Python, front end framework used is Flask, backend framework used is Jupyter Notebook, database used is SQLite 3, and front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working models of law of work. So the first step is importing required packages. So the initial step involves importing essential packages such as NumPy, Pandas, Matplotlib, sklearn, TensorFlow, and Keras. These form the foundational tools for data manipulation, visualization, and machine learning, creating a robust environment for subsequent tasks. The second step is exploring the dataset. So, the dataset exploration phase encompasses reading and plotting images to gain an understanding of the data. The third step is image processing. So, this step involves pre processing images, including converting them to blob objects, defining classes, declaring bounding boxes, and converting arrays to NumPy arrays. These processes prepare the images for subsequent stages in the computer vision pipeline. The next step is loading the pre-trained model. Here, the pre-trained model is loaded and its network layers are read. Output layers are extracted, setting the stage for utilizing the pre-trained model for object detection tasks. The next step is image processing again. So, further image processing involves appending image annotation files, converting color spaces, creating masks, and resizing images. These steps ensure compatibility and optimization for the subsequent phases. The next step is data augmentation. In this step, data augmentation techniques such as randomizing, rotating, and transforming images are applied. These augmentations enhance the model's ability to generalize and improve its performance on diverse datasets. The next step is installing the packages required for YOLO v5 in Colab. Here, the necessary packages for implementing YOLO v5 in Google Colab are installed, ensuring a seamless integration of the YOLO model for subsequent data processing and training. The next step is processing the data based on YOLO v5 model. So the dataset is processed in alignment with the YOLO v5 model requirements. This includes organizing and formatting the data to match the model's expectations, ensuring optimal training performance. The next step is training and building the model. In this step, multiple YOLO models, including YOLO v5s, improved versions, and MCS YOLO v5s, along with other established models like YOLO v4, YOLO v3, YOLO v3 Tiny, YOLO v7, FASTA RCNN, and AD FASTA RCNN, are trained and built. This involves fine tuning the models on the specific dataset to improve object detection capabilities. And in the next step, as an extension, exploration of additional models such as YOLO V5 by 6 and V8 is conducted, aiming to enhance the robustness and accuracy of the final predictions beyond the initial set of models. And as an extension again, a front-end interface is constructed using the Flask framework, incorporating SQLite for user sign-up and sign-in functionalities. This user-friendly interface allows users to input images, triggering pre-processing and detection using the trained models. So the front end facilitates user testing by accepting image inputs. The input undergoes pre-processing and is fed to the trained models for detection. And the final outcomes are displayed through the front end, providing a user-friendly experience. Now we'll understand about the algorithms used. So the first algorithm built is YOLO V5S. So YOLO V5, that is You Only Look Once version 5, is an object detection algorithm known for its speed and accuracy. It divides an image into a grid and predicts bounding boxes and class probabilities for each grid cell. YOLO V5S refers to the small version of the YOLO V5, balancing performance and efficiency. The next algorithm built is YOLO V5S improved version. So this includes enhancements over the base YOLO V5S in terms of architecture modifications, training strategies, hyperparameter tuning. Improvements aim to boost accuracy and efficiency in object detection tasks. The next one is MCS YOLO V5S. So MCS YOLO V5S introduced in this project incorporates a coordinate attention module for spatial and cross-channel information aggregation. Additionally, it employs a multiscale small object detection structure for improved sensitivity, enhancing dense small object recognition. The next one is YOLO V4. So YOLO V4 is an evolution of the YOLO series, emphasizing speed and accuracy. It introduces features like CSP Darknet 53 as a backbone, PANNet, and a same block for improved object detection. The next algorithm built is YOLO V3. So YOLO V3 is an earlier version of the YOLO series characterized by a three-stage detection process. It employs a Darknet 53 backbone and predicts bounding boxes at different scales. YOLO V3 balances accuracy and speed in object detection tasks. The next one is YOLO V3 Tiny. So YOLO V3 Tiny is a lightweight version of YOLO V3 optimized for faster inference on resource constrained devices. It sacrifices some accuracy for improved speed, making it suitable for real-time applications. The next one is YOLO V7. So YOLO V7, an advanced iteration in the YOLO series, integrates features from YOLO V4, scaled YOLO V4, and RYOLO. Its core, the Extended Efficient Layer Aggregation Network EELAN, enhances learning, and compound model scaling allows independent adjustment of width, depth, and resolution. YOLO V7 excels in real-time object detection, making it a fitting choice for the project's demands, with its balance of efficiency, adaptability, and accuracy. The next one is FASTA RCNN. So FASTA RCNN, that is region-based convolutional neural network, is a two-stage object detection framework. It proposes regions of interest using a region proposal network, that is RPN, and classifies those regions. And the last algorithm built is AD FASTA RCNN. So AD FASTA RCNN, that is Adaptive Dynamic FASTA RCNN, enhances the FASTA RCNN object detection by incorporating a dynamic region proposal network, a visual attention scheme for better feature generation, and an adaptive dynamic training module, enhancing adaptability and overall object detection performance. Now we'll see the comparison graphs. So this is the horizontal bar graph comparing precision scores of different algorithms. In this graph on x-axis, I have precision scores, and on y-axis, I have algorithm names. Precision measures the accuracy of positive predictions, representing the ratio of true positives to the sum of true positives and false positives. This is recall scores comparison graph. In this graph on x-axis, I have recall scores, and on y-axis, I have algorithm names. Recall assesses the model's ability to capture relevant instances, calculated as the ratio of true positives to true positives and false negatives. And this is MAP scores comparison graph. In this graph on x-axis, I have MAP scores, that is mean average precision scores, and on y-axis I have algorithm names. So MAP evaluates object detection performance by calculating the average precision for each class and then determining the mean over all classes. So the algorithm which is best performing in all the performance metrics will be used for predictions. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And in these folders, I have the required dataset. In this folder, I have images on which we will make the detections. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. And these are model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. And these are Python main code files. This is Notebook Jupyter source file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file explorer. I'm copying it. Open Anaconda prompt. So now use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, local host, and port unless configured differently. So this is the local host and this is the port. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. So if we are new users, we have to register first. Fill in all these details and click on register button to sign up. And if we already have an account, we can directly log in by clicking on this link. So as I already have an account, I'm clicking on this link. So here we have to provide our credentials, username and password and click on login button. So it has redirected us to the detection page. So now we have to upload an image and the application will detect the objects in the image. Click on choose file button. So from sample images folder, I'm selecting this image and click on open. So the image is loaded. Now click on upload button. So here we can see the application has detected the objects and drawn a bounding box around the objects. We can also see the classification of the detected objects as bus. And we can also see a probability score which tells us how confident the application is about the detection. Click on back, we'll try again. Click on choose file button. This time I'm uploading this image and click on open. So the image is loaded. Now click on upload button. So here we can see the object has been detected. The application has drawn a bounding box around the object and we can see the classification of the object, that is train, and we can also see a probability score. Now click on back. We'll try again. Click on choose file button. So this time I'm selecting this image and click on open. So the image is loaded. Now click on upload button. So here we can see the application has detected this object and classified it as traffic sign. Click on back. We'll try giving another image. So this time I'm selecting this image and click on open. So the image is loaded. Now click on upload button. So here we can see the application has detected the objects and drawn bounding boxes around the objects. So it has detected the traffic light, the truck, car, the rider, motorcycle, and we can also see the probability score telling us how confident the application is about the detection and the classification. So similarly, we can upload any image and can get the detections and classifications. Now click on sign out. So the conclusion here is this project is emerged from the critical need to enhance the safety of autonomous driving because of the escalating challenges of accidents and congestion. We aim to revolutionize environmental perception systems using deep learning, contributing to the advancement of autonomous transportation. So the project involved the development of various algorithms including YOLO V5S, an improved version, the innovative MCS YOLO V5S, comparative analysis against benchmarks like YOLO V4, YOLO V3, YOLO V3 Tiny, YOLO V7, Fast RCNN and AD Fast RCNN was conducted. And as an extension, we explored advanced models such as YOLO V5 by 6 and V8 to bolster the accuracy and robustness of our final predictions. The integration of Flask framework with SQLite for user testing coupled with user authentication provided a seamless and secure front-end experience for users interacting with the autonomous driving system. And the project's ultimate beneficiaries are the users and communities engaging with autonomous driving technology. By prioritizing safety through improved responsiveness, our project contributes to reducing accidents, enhancing transportation efficiency, minimizing pollution, and fostering broader technological advancements in the realm of autonomous transportation.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.